Okay, this is section 14.2 on limits and continuity. So in R2, if you remember, this hole here is called a discontinuity. And this is the removable type. Everything else kind of it tends to be analogous. So even though our function evaluated at A is undefined, the limit as x approaches A of f of x is, in this case, L, the y value. And the reason that's true is because the limit as x approaches A from the negative side is L, and the limit as x approaches A from the positive side of f of x is also L, and if those limits are equal, then the limit ultimately is equal because you're approaching from every possible direction and you're still approaching that same number. So things get a little bit more complicated in R3 when our functions are of the form f of x, y, and they are surfaces instead of curves. And so that adding of the dimension means that now our approach must be L from all angles. So meaning that if we're going along the surface from here, we have to approach that L value, that Z value, or here, or any angle in a whole 360-degree rotation, they all have to equal the same limit. So proving these is a little bit harder than in R2, and so we'll mostly just do examples of things that don't have limits. But just like in R2, the first thing you do is try substituting. That's the first thing that you want to do. And let me see if I have an example of that. Let's just do a quick one. If, let's say our function, whoops, I want to go with the limit here. If the limit as xy, remember we have a two-dimensional domain now, so now it's not just x approaching 0, it's the point xy approaching the point 0, 0 of x squared plus y squared, let's say. There's a function in two variables. Well, that's just 0. And that's because f of xy is continuous at 0, 0. So when we're computing these limits, the first step is always to just try, if it's continuous at that point, if there aren't any discontinuities, and go ahead and plug in. Well, the other thing that we're going to do here is basically we will show, or I'll say that we can show, that a limit does not exist. I'm going to add otherwise to that, because we can show that the limit exists if the function, if the surface is continuous at that point. But otherwise, we can show that the limit does not exist. Showing the limit does exist, at a discontinuity requires using the definition. And that's out of the scope of this class. I'm not going to write that out. I'm just going to say it. Okay. You guys probably remember the delta epsilon definition of a limit in R2. The three-dimensional one is similar. Okay, so let's do an example. Let's find the limit as xy approaches 0, 0. Of sine x plus cosine y. So these are both continuous functions. Sine and cosine are both continuous functions. So to do this, we're just going to plug in. So if we plug in 0 here and 0 here, we're going to get 1. And so this one was continuous, so it had a limit. Next example, let's take the limit as xy approaches 0, 0 of x squared y squared over x to the fourth 3y to the fourth plus 3y to the fourth. Okay, so we could look at the graph of this. Maybe we'll do that after we finish. But the way to approach these problems is to just literally approach at different places. So I'm looking just at the domain here. I'm just looking at x and y. And here's 0, 0. And what we can do is we can approach it from x equals 0. So let x equal 0. That would be along the y-axis. So then the limit, we could do 0y approaches 0, 0. So notice we're just freezing the x direction at this point and taking that out of the equation. So then we're going to get 0 over 0 plus 3y to the fourth, which is 0. Now, I want to just take a moment to point out that this isn't 0 over 0. This is 0 over something approaching 0. So it's not the indeterminate form. And then we can go and let y be 0. So let's see, x comma 0 approaches 0, 0. And then what we're going to have is, again, 0 over x to the fourth plus 3y squared, whoops, to the fourth. I'm sorry, this last part was supposed to be 0. Which is, again, 0. Okay, so far we're nowhere. But once you let x be 0 and y be 0, the next thing that is typical to try would be let y equals x. So then our limit becomes the limit as xy, as xx approaches 0, 0. And if we replace y with x, then we're going to have x to the fourth in the numerator. I'm looking up here. X to the fourth in the numerator because we have x squared times x squared. Then we have x to the fourth plus 3 times x to the fourth. So that is going to be over 4x to the fourth. And that limit is 1/4. Since the limit varies by approach, the limit doesn't exist. And when I talk about the limit, I mean the original limit. In other words, this limit really is 1/4. Okay, and these limits really are 0. But since they're not equal, this original limit that we were interested in does not exist. So let's do one more. This should be example 3. And we want to look at the limit as xy approaches 0, 0 of x squared y e to the y over x to the fourth plus 4y squared. So if we let x equal 0, then we've got the limit as y approaches 0. I'm kind of, if I'm letting x be 0, then I'm going to have 0 over 4y squared, which is 0. Since I've let one of my variables be constant, this notation is okay for this particular iteration. So let's do y equals 0. And so we're going to now let the limit as x approaches 0 of 0 over x to the fourth, which is still 0. So again, let's try y equals x. And now we're going to have the limit. I'll change everything to x as x approaches 0. And then I'm going to have x cubed e to the x in my numerator. Again, I'm looking at this right here and just replacing the y with the x. And then if I replace the x with the y, those aren't like terms, so I'm going to have x to the fourth plus 4x squared. And this is this to 0 over 0, which is indeterminate. But we can use L'Hopital's. Which says that if we look at the ratio of the derivatives, that will also be equal to the limit. And the reason that works is because when you take the derivative, you're looking at the rate of growth. And when we're taking a limit of a fraction, we're looking at the relative rate of growth of the numerator and the denominator. If the numerator and denominator are moving at the same rate, we're going to get a constant. And if the numerator is getting to 0 faster than the denominator, then we have 0. And then if the denominator is going to 0 faster than the numerator, then we have infinity. So we'll need L'Hopital's to clear that up. And then that's going to require us to use a product rule. So let's see. I'm going to go over here. And do the limit as x approaches 0. So for product rule, so we're taking the derivative of this numerator here. So we do x cubed times the derivative of e to the x, which is just e to the x, plus 3x squared times e to the x. And then for the denominator, we get 4x cubed plus 8x. And this is going to be 0 over 0 again. This feels like it might give us problems, so why don't we just try a different approach? And the thing I'd like to point out here, by the way, if you keep going, you're going to end up with 0 on this one. But it's worth trying a different approach. Now, this one, the next one that is like your typical approach to try is y equals x squared. And let me show you why this one is going to work. And that's because this y squared and this x to the fourth, one of our issues is that those aren't like terms. But this substitution will facilitate that. So let's go ahead and do that one. We've got the limit as we're going to change everything to x, so x will approach 0. Remember, we're replacing y with x squared, so we're going to have x to the fourth e to the x squared over x to the fourth plus 4x to the fourth, so that will be 5x to the fourth. And you can see that because those were like terms, now we could reduce and get rid of our, we don't have that 0 over 0 thing happening anymore. And e to the x squared is going to approach 1. Actually, it doesn't need to approach it. This is continuous at this point, and so then we just get 1/5. Therefore, the limit doesn't exist. And that's it for this section. This is a nice short